Okay, great. So let me start. So I have shared so every day, as you know, the lecture notes are being updated. So yesterday there was one update I made to the lecture one. So now those notes are updated on the central repository, wherever it is kept. So you have, and today, yesterday's notes are also up there. So 2 days worth of notes by Shushma are there. Also, I have been writing up, taking up the discussion that was had in the tutorial session. So yesterday, of course, the tutorial included my some more of what I said, that every object has a finite filtration whose subquotients are highest rate modules. That's what I in the tutorial. So that is part of the notes, and then the rest of it, and then the rest of it is in the tutorial. That was sort of trying to prove that the category O was Artinian. That I have not included, but the fact that you can use the Noetherianness of UG to show that every module, every submodule of finitely generated module is finitely generated. So that part I have actually typed up at length. So you will see Hilbert basis theorem, and then also you will see this properties of Noetherian modules, and then this fact that category O is closed undertaking subobjects. All of that from the Noetherian perspective is done in the tutorial notes, which should appear online on that central place if they have not already. So today we continue with what we were doing last time. Okay.
I will check, Apoorva. I will just check and then I'll upload. Yeah, if not done already.
Yeah. Thanks.
Yeah.
Okay. Yeah. Okay. Laptop at one place, but fine. I'll get my laptop when I need it. Okay. So last time we were looking at properties of category O. So we saw last time. We saw that category O is closed under various things. So first of all, we defined category O. Then we said some basic properties. One is let's see. The Verma module was the only thing I remember. Well, closed under finite direct sums and quotients is fine. Weights are inside weights. Weights are inside a finite union. So j equals 1 to k. Let's say lambda j minus the cone minus positive sums of roots. Sorry, positive sums of positive roots. That's all we did actually. And then we did finite filtration of the highest rate modules. Filtration of chain of submodules, whatever, whose subquotients equals highest rate module. That was what we said. And then we also saw, for as a, sort of these examples, for example, ML over SL2. So ML is equal to this nice module that we saw. UG, G is SL2. That's 1, if you will, by the left ideal UG times e power L plus UG times. Maybe this is what I will now call ML comma lambda. Okay, so I will also use lambda. Lambda is an H star, or lambda is a scalar roughly. H minus lambda of H. This module will keep showing up. So it's a nice example. And yesterday we talked about the fact that Raghuram in the audience had asked the question that does it get generated by always does every object of category O get generated by maximal vectors? And in this particular case, if lambda is not equals minus alpha, then the answer was yes. This was generated by two highest rate vectors. Generated by highest weight by maximal vectors. E times 1 and Fe plus lambda plus alpha of H times 1. If lambda is not equal to minus alpha. Whereas if lambda equals minus alpha, then this becomes 0, so it still sits inside E times 1. And then the vector 1 never gets, the image of 1 never does not lie inside here. Image of 1 lies inside the module, but it is not going to be generated by a maximum. Okay, fine. So these were the two, let me just call. So we just saw these two things. So that was the end of the recap. Let us now continue. Okay, so now so more basics. Continuing with the basics, here is the next, I'll just call it a lemma, or maybe a corollary. Yeah, I should call it a corollary. So we already saw some properties, like the weights of every object lie in the finite union of these cones. These are called cones. Because they look like lambda j and then minus like that. So that looks like a cone. So they're called cones. Okay, so the corollary, so yeah, these are two properties we said. The corollary is that every object of, I'll just call it M belongs to O, but of course you should remember categories, objects don't form sets necessarily. Every M in O is it's semi-simple, of course, with finite dimensional H-weight spaces. And the proof is sort of two lines. That's why it's a corollary. Write down this filtration. So there exists a finite filtration. There exists a chain. 0 equals M0 contained in M1. Let's say M K equals M. These are just chain of G modules, not modules in O a priori, because I don't know that submodules of O are in O. Now, if you read the homework or tutorial notes, then it is true, but I will prove it in a different way today. So there exists a chain of G modules such that all the subquotients Mj mod Mj plus 1 mod Mj is the highest rate mod. So, for example, let's say the Varma, it's of highest rate mu j. For all j available. Now, because M itself is semi-simple, so of course, basically the idea is as follows. If you want to take the lambda weight space of M, then that is the sum of lambda weight spaces of all these, of all the of M0 and all the differences. So each difference is just a highest rate module. So okay, so now so for every lambda, and because M is it's semi-simple, and so are all the MJs. That we saw last time, right? And hence Mj mod Mj plus 1 as well. And Mj plus 1 mod. All of these modules are semi-simple. So because of that, maybe let me not put the so for each lambda. In this happens, hence for all lambda in H star, the dimension of M lambda is literally going to, oh, okay, I don't need to say 0 is of course. That's fine. Yeah. The dimension of M lambda is going to be the sum of the dimension j equal to 0 to k minus 1, the dimension Mj plus 1 mod Mj. This module's lambda weight space. It's all very predictable, but I want to write it down. So, and now the point is, this guy is a quotient of a Varma module. So therefore, that sum, or each term in that sum, is term by term less equals the dimension of the M mu j lambda. And now there are two cases. Either lambda is not of the form mu j minus a sum of positive roots. So if lambda cannot be obtained from mu j by subtracting positive roots, what is the dimension? Anyone? If you cannot apply lowering operators to the high state vector here and get to any weight of any vector of weight lambda, then what is the dimension of that weight space? Somebody? Nobody? That's just zero because there is no way to write. There's no way to write down mu j minus lambda as a sum of positive roots. Otherwise, it is literally just the constant partition function of, I guess, lambda minus mu j or mu j minus lambda. Did I write it for negative fluid rates or mu j less than? I forget what I wrote, but yeah, positive roots. Oh, okay. In either case, this number is a finite number. And there are only finitely many such finite numbers we are adding up. And that's what you want to do. So for all lambda in star, the dimension of n lambda is strictly less than infinity. Okay, so that is one more basic corollary. Okay, another basic corollary is every high squared module not equal to 0 has a unique maximal submodule and a unique simple quotient. A unique simple. Of course, the simple quotient is in O, and later we will see that submodules are also in O. But for now, the simple quotient is in O. So proof. Okay, let me prove this. So basically, let's give this module a name, call it B. So let's say suppose B is the highest rate m lambda. So say m lambda subjects onto B. By the way, I should point out that that lambda comes from the highest weight, from the weight of the highest weight vector, weight of the maximum vector. So there's some m lambda here, and then this goes to the maximum vector. So lambda is uniquely determined. I can't have two different m lambda subjecting down to the same highest weight module because the lambda is uniquely determined. Okay? So this lambda, m lambda subjects to be fine. Now the claim is the following. So note that. So if let's say n is a proper submodule, so n is a proper submodule, then certainly n is h semi-simple because that is we showed that if you have a diagonalizable bigger module, then you have a diagonalizable smaller module. So n is very semi-simple. So the weights of n, whatever weights eigenspaces occur here, of course, are contained in the eigenspaces here. So the weights, the eigenvalues that occur here are a subset of the eigenvalues here. Can you tell me one eigenvalue that does not occur in n? One weight that doesn't occur in n but occurs in B? We want at least one weight. I claim that there is at least one weight that occurs here. The weight space occurs here but doesn't occur here. Then there is only one weight written on the entire code. That had better be it. Then the claim is that n lambda is 0. Why? Because what is the dimension of V lambda? What is the dimension of the highest weight space? That we have seen. That's basically the same as it's at least 1 because this vector is there. And it is at most the dimension of m lambda's lambda weight space. But by the constant partition function, you can figure it out. This has a unique one-dimensional weight space. Maybe a note that I should point it out here. Maybe. Fine, I'll point it out later. Very fine. I'll point it out first and then write this sum. Note that 0 is less than the dimension of V lambda because V lambda includes the weight space with the highest weight vector, and that is less equal to the dimension of M lambda weight space. But again, what was M lambda's lambda weight space? This is exactly Cm lambda. Because everything else you have to apply at least one strictly lowering operator. So the weight goes down lambda minus some alpha I or minus alpha I minus alpha j or so on. So you have to apply at least some lowering operator. So therefore, this is just this, which is 1. So this dimension is strictly bigger than 0 and less equals 1. So it's 1. So basically what we are saying is V lambda is Cv lambda. So of course it's 1 dimensional. Now suppose you have any proper submodule. If n is proper, then n lambda has to be 0. Why? Because n lambda has dimension 0 or 1. It's a subspace. Remember that n is also x semi-simple. Then n lambda is either 0 dimensional or 1 dimensional. If it is 1 dimensional, then it contains the highest weight vector. If it contains the highest weight vector, it contains the entire module generated by the highest weight vector, which is all of V. So then n would not be a proper submodule. So I'm not explaining this, but therefore this is here. Yeah, I hope I'm not writing this down. I just explained it. But that's why this is 0. Great. So now once you have this, what do you do? To generate the maximal submodule, so define, let's call it n max. The name very suggestively is the sum of n, where n is a proper submodule of V. Just add up all of those subspaces. Now each of those subspaces on the right, submodules, is a H semi-simple vector space or submodule. So their sum is also H semi-simple, and take the unions of all the, take the sums of all the individual eigenspaces, weight spaces. This is a submodule of V. Maybe I'll just say this, and you can check that there is nothing bigger, because if this was not the biggest submodule, proper submodule of V. Okay, sorry, I should say this is a proper submodule. The fact that it's a submodule is obvious. Why is it proper? Can anybody tell me why it's proper? The answer is again on the board. May not be this board. Like may not be this half of the board. So why is this a proper submodule? And that's because, again, the same thing. Look at the lambda weight space of this module. When each of these modules has lambda weight space 0, so the sum has lambda weight space 0. That's why it's a proper submodule. Great. So now once this happens, therefore now it's a proper submodule, and I claim it is maximal. Because if you have any proper submodule of V, then it is already on this side and therefore contains. And by construction, N max is the unique. The moment you have a unique maximal submodule, you take the quotient, that's the unique simple quotient. Right? Okay, I should have mentioned. Does everybody know simple modules? Simple just means irreducible. There are no two. There is no proper submodule which is non-zero. It was that. Okay. Oh, while character formulas. Yes. So V mod n max is the unique simple quotient. So the point is to get a simple quotient module, you have to quotient by a maximal submodule. You can figure it out by. Okay. So therefore now this is the unique maximal submodule. So that's the unique simple quotient. And this is denoted by now the remark, which I will basically say it's quotient of quotient is quotient. The point is I start with any highest rate module of weight lambda, highest rate lambda, I get to some unique simple quotient. Maybe I could have started with a different highest rate module. Would I get a different simple quotient of that highest rate module? And the answer is no, because every submodule here lifts to a submodule there. So I'm not going to mention all this. This simple quotient does not depend on the choice of initial module as long as the highest rate is fixed. The initial choice of module m lambda to v as long as lambda is fixed. Sorry for the squeaky marker. I don't know why it's squeaking. Okay, that's part 2. Okay, now it's property 3. So let me write down property C. Sorry. So since it does not depend, definition, let's give that simple module a name. Call this is going on. Call this this was the new one. This one. Call this simple module L lambda. So L stands for the simple module, M stands for the Verma module. And remember that this simple module is a quotient of some highest rate module. Highest rate modules lie in category O. Therefore, this module under quotienting category O is closed. So this module lies in category and closed under quotient. Closed under quotient. Therefore, these are the simple modules in category. These are some simple modules in category O. The next basic step is that these are all of them. And they are pairwise non-isomorphic. So that I will write down.
Sir, excuse me. Could you please repeat why the summation of dimensions of m mu j lambda, lambda was 0 if you could not express lambda as an element of mu j minus non-negative?
I'll remind you of that. So remember what a Verma module is. A Verma module or any high shape. So m lambda, m mu j is the highest rate module. So it's generated by some vector m mu j, let's say. Weight is mu j. And ei m mu j is 0. And so what is it equal to? We saw already that this is therefore equal to it's un minus times uh times u, because it is generated by one vector, so it's the same as ug times m mu j, and ug by the PBW property is exactly this, right? Times un plus times m mu j. But now because n plus kills m mu j, right? We just said that. So what is un plus times m mu j? It's not 0. What is it? What is un plus? First, you have to think of that. What is un plus? Un plus, when the PBW theorem again has a vector space basis for all words in the positive root vectors, in the e beta 1, e beta 2. Fix some basis, fix some ordering of positive roots, take those corresponding positive root vectors, the set of words in this order, e beta 1 power something, e beta 2 power something, times m mu j is a basis. So now, but we know that every one of these guys is built out of these guys, so it kills m mu j. Every such word kills m mu j. So what is this equal to? Anyone, not just the person who asked me. So remember that, of course, there are all these words in here, but there is one extra word in here that is sort of hidden among these. The empty word. So the empty word is just e beta 1 power 0, e beta 2 power 0, e beta n power 0. And that is the only word that does not kill m mu j. So this guy exactly is the same as
m mu j.
scalar set m mu j. Now what is there for this guy? So I can replace this scalar by the scalars can go inside it. Now what is this much? So this was what I was doing on day one, I think, the recaps. So this is UH times MUJ is again scalars times MUJ because the weight is MUJ, which means that every H acts by a scalar. This is a simultaneous eigenvector. So every H in here acts by a scalar. So this is still scalars times MUJ. So really UG times MUJ is basically just this much. Okay? And now this guy here, again by the PVW theorem, you can write down F beta 1, F beta 2, F beta n as the basis of n minus. And this is the span of all, let's say, tuples k bigger equals 0. F beta 1 power k1, F beta n power kn, as n mu j. What is the, so clearly all of these guys are weight vectors for H for the entire pattern. What is the weight of this guy? So do you remember this part? F beta, or I well, that again is the thing I mentioned. UG of any monomial in UG of total weight beta, you act on any module's weight space or weight mu. This is contained in what weight space shape? Let's maybe even do that calculation. This is mu plus beta. Because if you take some vector m here and you take any vector h in H, let's look at what happens. So H times whatever x in UG. So I take x here, take m here, take h here. X times xn is h x minus x h acting on m plus x times h acting on m. But now I can, of course, this is a module thing over associative algebra. So first I act not x times h, but x acting on hm. This is h bracket x. And now this is x times m had weight mu. Therefore, this is mu of h. Is this clear that h times m is mu of h times m? Because m is in m mu. So that's the definition of m being in m mu. Any h in the Cartan algebra acts by this scalar. Okay. And this is just h bracket x. But h bracket x is what? Because h bracket x belongs to UG beta. Therefore, again, by definition, h bracket x is beta of h times x. And now here it is plus, I take the scalar outside, mu of h times x. This is beta plus mu or mu plus beta. So this is why if you take any vector in this weight space under the adjoint action, acting on any vector of weight mu in any module, the result falls inside this weight space. And you check it by applying any element of the arbitrary element of the Cartan subalgebra to x times m and checking you get the scalar times x times. So this is why this happens. Therefore, now what is the weight of this guy? If you understand this part, tell me the weight of this guy. I mean, somebody, anybody. So the point is, what is the weight of each individual guy? If you act by h on this guy, you will get kn times minus beta n. So it's mu j minus summation, let's say L goes from 1 to n, k L beta L. Okay. And that's exactly what the question was. So what is this? This is precisely, but these guys, beta L's are sums of, these are positive roots. So they are sums of simple roots with positive coefficients. So this belongs to mu j minus, I'm subtracting the bunch of sums of positive roots. I'm still subtracting positive roots. These are both bigger equal 0. That means I'm subtracting positive roots, but positive roots are sums of simple roots. So I'm subtracting sums of simple. So every weight of the Verma module is less than, start with the highest weight and subtract some positive. So every weight of this guy is in here. Yeah. Okay, I'm going to erase this line. So what I'm saying is, so all weights of MJ are equal to mu j times this for some choice of integer scale, but that means they all belong to this. So unless the weight was inside here, mu j does not have that weight space. So that means the dimension of that weight space is 0. Right? If some vector space doesn't have the eigenvalue 3, then what is the dimension of the 3 eigenspace? We don't say that the eigenspace doesn't exist. We say that eigenspace is 0. There are no non-zero eigenvectors in it, but the eigenspace still contains the origin in a vector space. So even if a scalar is not an eigenvalue of some operator acting on the vector space, it exists, but it still is 0. So by convention, again, if lambda was not inside this set, the eigenspace exists, M mu j lambda weight space, because the eigenspace exists and is 0. It's just okay. So I hope that answered the question. I'm going to erase this now because I will continue from here. That is later. Yeah, finite length. So Jordan, eventually we can just choose the Jordan. Okay, so we said this. So we have written down certain simple modules. For every lambda, the Varma module, I don't know what other high state modules exist, but the Varma module certainly does. So therefore, for all lambda n star, there exists a simple module. Okay, let's say there exists a unique simple module of highest weight lambda. Let's prove this. The existence comes from Varma modules. So m lambda surjects onto m lambda is a high state module. It surjects onto a unique simple module from here. It has unique simple quotient. That simple quotient also has high state lambda because the image of this guy, whatever this is the generating vector, is the maximum vector of it. Okay, how about the uniqueness? How about the uniqueness? So for uniqueness, what I say is the following. Right? So take any simple. Of course, unique simple meaning always up to isomorphism. You have to always write this up to isomorphism disclaimer. But so yeah, suppose you have a. This was done by Ravinder, I think. This was done already. Sorry? No. In Humphrey section 22, this is already there. Right? Am I right? Can anyone check? Just tell me if Ravinder did it. But I'm pretty sure in Humphrey section 22 it's there. Can you check? Do you have Humphrey with you? I have it with me. I mean, I was just going to say that, well, you take a simple module of highest weight lambda, the Varma module subjects onto it. So it's isomorphic to L lambda. But there is a different, where you use you take two simple modules, you take their sum, you look at the diagonal submodule, then you say each of them is isomorphic to that. So there is that's the other way to do it. That is in Humphreys as far as I remember. Check. Traces on weight spaces, blah, blah, blah. Freudenthal. No, this would be in section 20 and 21. Sorry. I don't need finite dimensional. Yeah, let VW be standard cyclic modules of highest rate lambda, which are irreducible, then they're isomorphic. This was already done. But now the claim is, so this was sort of okay. The claim is part, I could call this part C. That was part B was it? Fine, let's keep it only. Part C is that the proposition that the modules L lambda are pairwise non-isomorphic. So it is up to isomorphic. L lambda is not isomorphic to L lambda. Fine. The modules okay. So they are pairwise non-isomorphic. And exhaust all simple objects. Rather than say simple objects, I will say simples. So the standard way to write things is simples or Vermas or projectives, meaning simple modules or Verma modules or projective modules, but not highest weights. Highest weights is very different from highest weight modules. Okay, and exhaust all simple. So these are the only ones that are the simple ones. In category of proof. So okay, let's do each of them turn by turn. So let's say pairwise non-isomorphic. So say L lambda is isomorphic to L mu. I will prove that lambda equals mu. What does this mean? Isomorphic means there is isomorphism. Let's write down, i.e. there exists a phi in form G and lambda and L. I could take Hom G or I could take Hom in the category O because it's a full subcategory. The module maps are the same. Okay. So phi Hom G, L lambda, L. Then what do you know? Well, there is a maximal vector here which I will call V lambda. So V lambda has to map to something. So a phi of V lambda. Now, first of all, what do we know? Phi is a G module map, so it's an H module map. So it respects the weight. L mu lambda. But also, if you apply any raising operator, if you apply any EI here, then phi of EI, so EI times phi V lambda is equal to some EI times this, whatever this mystery. So I want to understand what this vector is over here. Well, this vector is first of all a weight lambda. But secondly, if you apply any raising operator, this is phi of EI V lambda because it's a module map. EI V lambda was 0. This is just 0. Phi of 0 being 0. Okay. For all r. So this is therefore a maximal vector in L mu. But then what do we know? Maximal vectors generate submodules, right? And by what I just said using those PBW reductions, U n plus acts by scalars, UH acts by scalars, so it's just UN minus. Is a proper and sorry, not proper, is a submodule. And not only that, because there's an isomorphism, this guy cannot be 0. right? What happens if phi v lambda is 0? If phi of v lambda is 0, then phi of anything times v lambda is also 0 because, yeah. Okay, maybe I'll say that. Okay, let me say this. And it is this module is not equal to 0. Why not? Because UG contains the scalar 1 and phi of v lambda is not 0. So phi v lambda is already there. It contains phi v lambda. I'm really spreading things out, but fine. The only question is why is phi v lambda non-zero? Let me just say it here, but I won't write it down. So if phi v lambda was 0, then phi of anything times v lambda, anything in UG times v lambda is that thing in UG times phi of v lambda, which is 0 again. So the entire module would be mapped to 0. If the generator goes to 0, then the entire module goes to 0 under the module map. But then how is this an isomorphism? The whole point was this was an isomorphism. If this is going to 0, then L lambda has to be isomorphic to 0. And that's false. L lambda is certainly non-zero. Right? So therefore, phi L lambda is non-zero. Therefore, this is non-zero. Phi of V lambda is non-zero. Therefore, the image of phi of V lambda, the submodule. But now here we go. We have a submodule, a non-zero submodule. Actually, why should I put it in brackets?
Sir, I think you have missed a phi there in the right hand side.
Say that again.
I think you have missed a phi in the right hand side.
Where? Here? Ah, here.
Yeah.
Right. So this is a submodule of a non-zero submodule of a simple irreducible module. There is only one such module, which is the module itself. As L lambda is L mu simple. So yeah, so this is. But now you can check, right? The point is this vector generates the whole module. Okay, maybe I'll say the following, right? So the weights on both sides are equal. Weights of LHS. Maybe I should just have said that to start with. I don't know. And in particular, generators. Well, so now from this you can check using the highest weight, if you will. That lambda is. Maybe well, maybe I should not even do that, right? I can maybe I should do it the other way. Maybe I'll make it simpler. Let's even. So all I want to say is that this. Therefore, lambda is again from what we saw in all of that board. Lambda belongs to mu minus. And then there is one question I will ask. So now I have done this for the isomorphism going from L lambda to L mu. But because it's isomorphism, one can do the same thing using phi inverse. And from that we get that mu is less than lambda, meaning it belongs to lambda minus x. By the same argument. But now you're subtracting some number of positive roots to get from mu to lambda and subtracting further some positive roots to get back to mu. Because the simple or subtracting simple roots. Because the simple roots are linearly independent, these two facts together imply that. Now, what is the question I'm going to ask in anyone's case? The question is, where did I use the fact that these are simple? let's take a look. Did I actually need the fact that they're simple, or could this be done for any two high-speed modules? Or what is going on? And maybe I should leave you to think about this. Maybe is there a gap in the proof? Is that what is going on? So let me just take you through the proof again, and then you can think. Let's suppose these are isomorphic. So suppose there is a map going from them, right? And actually, sorry. This is probably where you use the fact that they are simple. Right? I mean, the fact that there exists a map is the same non-zero map. It's the same as the fact that the modules are isomorphic. That uses something has to be simple. Otherwise, the fact that non-zero map is the same as isomorphism isn't true for arbitrary items. Yeah. Then you take a that basically means the generator of the high-speed vector cannot be zero because this map is not zero, and it of course maps to a maximum vector in here of weight lambda. But then that means that I think that was enough. I did not need to say all of this. I can use this. Okay, fine. So that was one part. The more interesting part, of course, is this one, the exhaust all simple. Say L equals simple object in O. How do I prove that L is actually of the form L lambda or L? The point is the following. Let's look at the weights of L by O or by some corollary or previous basic argument. The weights of L, because L is object of O, are contained in the union of lambda j minus something like this. So among the lambda 1 through lambda whatever k, choose a vector that is not that is maximum. Maybe I should really look at this. I really need to define this partial order. So maybe we should first write down this partial order. So please put it somewhere. Define. We say. Did I say this already? Not. This partial order if lambda minus mu is a positive sum of simple positive forces. So this is clearly reflexive. You can check that it's symmetric because that's exactly what we're saying here. Because delta is a resist and it's clearly transitive. So it's a partial order. Sorry, it's anti-symmetric, what it's called. This is anti-symmetry, reflexive and transitive is easy. Anti-symmetric, transitive. Okay, so now all I'm saying here, so I will just start saying less equals rather than So choose lambda, so choose j such that lambda j is maximum among lambda 1 to lambda k. Then the claim is that there is no vector, there is no weight inside this entire union of sets which is bigger than this in the partial order. That's easy to check because I mean, the biggest vectors among them were these guys. Among these, I'm choosing a maximal one. So there's nothing else bigger than that. The claim is therefore then this lambda j, then lambda j is sorry. So first of all, so if I look at L lambda j, this is not equal to 0 because it's one of the weights. Oh, sorry. No. I don't choose these guys. But because of this kind of, the weights of L lie somewhere like this. Himalayan range. Lambda 1, lambda 2, lambda 3 maybe. And the weights of L lie somewhere here. So you can certainly find a weight of L that is maximum. Okay? So choose, so there exists a weight. Mu, no, there exists let's say lambda, I'll call it lambda, that is maximum. Because you take some weight. Now, if it is not maximum, there is something higher than that. There is something higher than that. But ultimately, as you go higher and higher, you would end up exceeding one of these peaks, basically, in a finite amount of time. You can't do that. So the last time you are there is the highest possible weight. I'm not saying it is the unique maximum weight. That is only true in Varma module and so on. Module, but there is a maximal weight. It's one that cannot be improved upon in it under this partial order. Great. So now, so now what does that mean? And so if V lambda belongs to L lambda, then what can you say about EI times V lambda? What is the weight of EI times V lambda? By the things I erased when I wrote them down there for explaining. The weight of EI times V lambda is what do I put here? Anyone? Come on. Okay, so it's basically weight lambda plus alpha I. Again, by the same property. EI is in UG alpha I, V lambda is in L lambda, so lambda plus alpha I. But L lambda plus alpha is strictly bigger than lambda. This was the maximal weight in here. So this eigenspace must be 0. So EI times V lambda is 0 for all I. And therefore now L lambda contains a highest weight vector. So L contains UG times V lambda equals the highest weight module, which subjects onto a unique simple portion. From this, you can deduce that L is itself equal to. I will leave it to fill up the details, but because we don't have so much time. But yeah, this is enough to deduce that L is isomorphic to L. Okay, so that was that. I wrote down like 4 pages, and I've just finished half a page of of things. So yeah, this cannot work. We have to go slightly faster. Okay. So the last thing then is, so now this is the main point of the first part of category O lectures, is the fact that every module has finite length. What does that mean? It means there's a Jordan. So this is where I will, I think, need my laptop. Or I can use, I might even already have that. 1 second. So there's a very fat book called Non-Commutative Noetherian Rings. And in the introduction section, page 2 or something, that was told. Here we go. On page 2. I need the most basic result about finite length. Okay, so let me just, okay. So this was number item 2 here.
No, 1C. No, this is C. That is 1C.
Oh, then I should say 2 here. So now finite length. Okay, so the point is, so what does length mean, first of all? Length itself means the following. Of course, obviously, highest weight modules and Varma modules are infinite dimensional. So that's not very, so that's not, it's just infinite. So that's not a very nice, refined way of counting things or keeping track of things. One thing that happens is in category O, the simple modules. So I remember we said that these simple modules are L lambdas, and so maybe I'll just start by motivating by saying most simple modules or simples in O are infinite dimensional. Why? Because the simple modules are L lambda. And this L lambda is finite dimensional if and only if. What do you know about lambda? For finite dimensional? Somebody said the injectivity needs the simplicity of L lambda. Okay, well, you can figure it out. Thanks. So what do you know about when is L lambda finite dimensional? This was again something that was done last week, right? The Weil character formula. Lambda belongs to P plus. Now the point is H star looks like a huge space, like a two-dimensional space maybe for SL3. And the dominant integral weights, these are the simple roots. So that means that the dominant integral weights are just these guys. There are only countably many weights. This is a countable set. Whereas H star, this is of course C power I, this is uncountable. So it's many more simple objects are infinite dimensional. Very few, only countably many, finite. So most simples are infinite dimensional, so most objects are infinite. Maybe let me not say that yet, because that's the whole point of proving this of this section. But so anyway, so the point is the dimension of an object is not a very useful way to keep track of what is going on. What is useful is how many simple objects go into a chain of submodules. So when you can write down every module in some decreasing chain such that the quotients are highest weight modules. But even there, can you refine that chain so that the quotients are simple? So to keep track of. That's a very imprecise question. So let me just say that is there any finiteness around? Sorry, oops. Okay. Is there any finiteness around? Somehow. Meaning by some different method. And the answer is yes, and that's what we are going to talk about. So the point is, first let me tell you a cruder answer, e.g. what we already saw. Every M in O has a decreasing chain whose subquotients are highest weight modules. As a chain, maybe has a decreasing chain, whose subquotient of submodules whose subquotients are highest weight modules. But highest weight modules themselves can have, like we don't know how many modules sit inside highest weight. So we are going to define this. So we will now define. Let me just say we will now define all such. But the length is still finite. So that's distracting from but we haven't defined length. Now let me do that. So the point is this. We have a chain of submodules, 0 to M0, M1, M2, and so on. And the subquotients are highest weight modules. Can you refine this chain? So we'll refine such chains. So I.e., if you question what is so given m in O, consider all possible chains of submodules without worrying what the subquotients are. Consider this is chains which are ascending chains. As well as, you can guess the next one. I'll call it m prime 0. Yeah. These are called obviously descending chains. Just of submodules. Okay, they don't need to be in category O or anything. Of course, in retrospect, they will all be in category O, but that's what we are trying to prove. Okay, so these are what these submodules are. The question is there can you keep finding larger and larger ascending chains or larger and larger descending chains? Or is there some kind of a uniform upper bound? For every module M, is there a uniform upper bound? I'm not saying that there is a bound for all objects in category O, but just for every module M. Is there an upper bound on how long these chains can be? That is the question. Okay. So first of all, okay. Now, as I said, maybe I'll point out the remark. There does not exist a uniform upper bound that works for all of category. Somebody should give me an example. Somebody should give me a proof of that. Why is there no uniform upper bound that works for all possible objects in category of such a chain length? Either ascending or descending. Somebody. So basically what I'm saying is, given say upper bound n, can you find the module with a chain of length n plus 1 for every n? The answer is very easy. That's what I'm asking. So somebody should tell me the easy answer.
Direct sums of modules.
All you do is remember that category O is closed under taking direct sums. So all you, for example, you take the trivial module, which is dimension 1, and just take L0 plus L0 plus L0. Say n plus 1 times. This is dimension n plus 1, but more importantly, at each point you can just kill off one summand, and that just gives you a chain of submodules as a chain of length. Length strictly bigger than n or all n. Therefore, the moment you have n plus 1 summands, it has a chain of length strictly bigger than n for every n. So there is no upper bound that works for all of category O. But for a single object, I claim that in fact there is such upper bound. And the idea of the first thing among what we do today is to going to be able to calculate the upper bound in some sense. We will calculate the upper bound for Varma modules and for all high-straight modules as a result. Okay. See, so now, okay, so before I calculate such upper bound, let me write down. So now let me tell you about the Jordan-Holder theorem. Okay, and that is what is the point where we are getting to. So maybe I should say the following, right? Suppose I have such a chain. Let me tell you how to improve on the chain. Then I'll tell you Jordan. Or if Amit is in the audience, have you told me about Jordan-Holder theorem, etc. already? Amit, Amit is in the
I already used it, yeah, without without
Okay.
mentioning, because this is a simple thing to do.
Yeah, I know. I'll do. Okay, so suppose you look at a chain, either ascending or descending. So how to what do I call it? Lengthen the chain. How to make a chain longer? And this is not the Akbar Birbal story where you draw a shorter chain next to it so it becomes longer. No. How to concretely make the chain longer? So basically, the idea is the following. Suppose I have some m, so it is longer, meaning I have to insert some extra terms between the sub. Right? I have 0 that's contained A, B, contained C, and contained M. So I know M is here, I know 0 is here. I want to make the chain longer. That means I have to insert some module in between. So say A between B and something like that. Now, how does one do that? That's what I'm trying to say. So this happens in the following way. This can be done. So let me in fact write that example, right? Draw that picture, 0 to 8 minutes. This thing. So this can be done at this stage, A to B, right? So this can be done between A and B. If and only if, very, very precisely, B over A, these are R modules, right? These are of G modules. If and only if B mod A is not simple. Right. Right? So that is what I'll just quickly explain. Proof, so claim, proof. So let's say this can be done. So if A, so these are of course all not, these are strict inclusions. I could put dot here, dot below, wherever. I just care about expanding it at lengthening the chain at a single inclusion. I can insert intermediate module. So if I have, since I have A, this can be done. So say A in B, then what does it mean? Then it means that B mod A is, first of all, it's a non-zero submodule because D is not equal to A. Second of all, this is contained, not properly contained in D mod A because D is properly contained in D. So therefore, this module, this quotient module cannot be simple because it contains a non-zero proper submodule. And conversely, suppose B mod A is not simple. Say B mod A is not simple. What does it mean for a module to be not simple? It means it contains a proper and non-zero submodule. What are non-zero submodules of B mod A? They look like D mod A for D, a lift of some module containing A. But the moment this happens, then it's just a like almost trivial. No, it is trivial, not almost. So you can increase a chain only when the quotients are not simple. So that's really the ideal situation where we are trying to get to. Can one start with any chain and refine it enough so that every single successive ratio, subquotient, is simple, is of the form L lambda? That's really the question. And now here is a sufficient condition. Actually, it's necessary and sufficient, and that's what Amit has already used. This is called the how to make a chain longer. This is true. So when does this work? when is this possible? So this was question 1. Krishna, what is the number?
2 without AB.
2 without A. Oh God. Okay, let's put this as A. This is B. Question 2 is when is this possible? So when is it possible to create a longest chain? A chain, and what by longest chain I mean that longest chain is a chain where all mj plus 1 mod mj are simple. This is a very general question because, of course, Amit, when he did his module, he was not talking over Lie algebras. He was not working with G modules. He was working with possibly non-commutative rings like UG modules over that. But any arbitrary, right? So the point is, this is the theorem, a very famous theorem. Which, if you haven't seen, you should. So I will write it down. And this is the theorem from page 2 of this book, non-commutative Euclidean rings. And this is
Maybe
called the
I should
Jordan.
ask you at this point, like, do you also have Krull-Schmidt property for this?
Yeah, we have. What is the Krull-Schmidt property?
Every
I just-
module is finite direct sum of indecomposables. No, I don't think you have that,
That's
right?
also from these things, I thought, right? I mean,
You prove it from this using
Huh.
Jordan-Euler for certain categories, but
category indeed is true. It is finite length category. So yeah, in fact, it is.
okay.
Yeah.
Fine.
So I'm going to tell you this, that I will tell the theorem. There is a uniform bound over the chain, and I will compute that bound for my Varma modules. The goal is to
Okay.
compute that bound for modules, and in particular, all this goes through. Yeah.
Okay.
Right. So, okay, maybe first I should define the. I'll just remind, and I won't write this down. This is called the ascending chain condition, which is that every ascending chain stabilizes. So if you write down, okay, fine, maybe I'll say this. A module is said to have ascending chain condition. And so R is some ring. And our module M has the ascending chain condition, which I will abbreviate because I have already put that in the tutorial notes. This is defined beside the tutorial notes, and the Noetherianness and lots more is done. So I'm not writing it down. If every ascending chain, which I had written on the previous board, stabilizes. Okay. Stabilizes meaning 0 to M1 contain M2 contain M3 contain M4. You write an infinite sequence of submodules. There is a finite stage beyond which all the inclusions are equalities. It is like M5 equals M6 equals M7. You can't go higher. Maybe that is equal to all of M. Maybe it is not. But the chain stabilizes. And similarly, a descending chain condition starting from M bigger than M1 bigger than M2. M has BCC. I will not even write this. I won't even write the thing that I did not write above. I won't even try to write it. Okay, so I'll leave it to you guys. Shushma can probably complete it in the lecture notes. Yeah, we will write it in the lecture notes. I think I will skip because I want to complete the application of this fact to our setting, that every object is finite. Okay, so now the point is we don't know in our situation for modules over UG in category O or yeah, we don't know that these conditions hold. We are asking if maybe they hold. Here is what we do. So here is the theorem that provides a characterization when both of these hold. So this is the famous Jordan-Muller theorem. And I thought I should write this down because it has been probably decades since I myself saw the statement. So nothing else than for my own sake, I'm writing this down. Jordan-Muller theorem. Okay, 2 parts. And yeah, M has both the ascending chain condition or satisfies whatever and descending chain condition together. If and only if there is such a bound. This bound. There exists n bigger than 0, such that I can take n bigger equals 0. N is the 0 module, then certain has ascending and descending chain condition of length 0. On the lengths of chains of some. All ascending and descending chains of submodules, or I don't even need to say ascending, descending. You create whatever chain you want. You start somewhere, go up, go down, what you want. Okay. Of submodules in M, R of length have length at most M. So M satisfies both the upward and downward stabilization properties if and only there is a uniform global bound on all possible chains of submodules. And if this happens, if so, or if this happens, if this holds, then every chain, if this holds and n is sharp and n is attained, right? So that means n is the least possible and it is attained. It's a finite integer, right? Then every chain of submodules you can refine it, or you can make it longer. Every chain of submodules can be defined to one of length n, to have length n. By length, let's say I mean the number of subquotients. Okay, so 0 module is just 0 and m0 are the same, so there are no subquotients. So 0 subquotients. Length is 0. For simple module, the length is 1 because m0 is m is 1, m and then 0 is 0. So 1 subquotient, the length is 1. So by length, I mean the number of subquotients. So there are n plus 1 terms. This means I mean 0 equals m0 containing double dot, m1, let's say, strictly contain mn, and mn is equal to n. There are n many subquotients, length n, and each subquotient is okay, and then I'll mention put a comma, not a full stop. And the subquotients mj plus 1 mod mj are simple. All of these subquotients are simple. A simple module. So this is the condition I mentioned. They have no proper non-zero submodules. And if you look at the set of all these n, maybe I can write two different such chains where those simple submodules occur in some other in a different order. But the set of all these simple submodules, simple quotients, are exactly unique, counting multiplicity and permuting the order in which they occur. So this is saying they are simple and uniquely determined up to order and maximum. And uniquely determined or unique up to order, meaning up to order, ordering and isomorphism. So this is the Jordan-Holder theorem, and this is what we are going to use now to guarantee that every object has finite. And so the moment you have this, we say length is n, finite. And so as I said, the length is precisely the number of simple quotients that occur inside any maximal chain of subquotients. So now the claim is, so now let me write this down. Here, so this is the theorem for today. Category O, all objects in category O have finite length. This is what we have to prove. That is where I will stop. Okay, 10 minutes is more than enough, but hopefully. But yes, this was all just one page, which is sort of disturbing. Okay, this is fair. And I wrote down the, as I said, I wrote down the, please 4 more questions. I have to go faster. Okay, fine. So now why is this so? So I want to show this kind of. Now what we already know. So I want to sort of say that you take any chains and then you have to expand it, right? To refine it and you still reach a certain length. We already know that m you can write down as a finite sum. So you can say maybe I'll write it in the way that 0 is m0, m1. We can do this. Where all the subquotients are highest weight modules. True? For all m in O, we can write this thing with all mj plus 1 mod mj with let's just maybe I'll just say it directly, m of mu. So it's a highest weight module. This is the highest weight for all j. Okay. So what I should be really doing is I want to now refine every one of these guys. Remember the claim that I wrote down, the trivial claim. When can you refine or lengthen this chain? You can do so if and only if the quotients are not simple. So I want to refine every such successive ratio into a chain where the quotients are simple. So all I'm saying is therefore it's enough to solve. So need to refine let me write it in words. Right. Need to refine this chain at each inclusion where this subquotient mj plus 1 mod mj is not simple. So in other words, right, it suffices to say that every highest weight module has finite length. Because if I take this highest weight module here, m2 mod m1, to show it has finite length, I want to refine it like that. So if I can refine every step of the way, meaning I can refine every such ratio, then I'm done refining the whole thing. Okay. So that's all I will just sort of say. So enough to show. ETS stands for enough to show. Maybe I'll say so colon enough to show every highest weight module has finite length. But now, let's see, what do I want to say here? This subjects of the. No, that I will say later, but I want to say that every Verma module is finite length. Okay, so then let's write this down. Let's say m mu. I'll call it m lambda. First, I'll say m mu to v as for every such v is finite. Right? But so this is how you talk about finite length and the set of Jordan-Holder factors are unique up to reordering. Is this Jordan-Holder theorem? It's a fundamental theorem in module theory. And as representations are modules, so it's an algebra, it's a fundamental theorem in representation. Whether you take finite dimensional algebras or infinite dimensional algebras, doesn't. If you're talking of finite length, then this is the theorem to use. Now, if I want to say somehow, so the point is this. So let's say 0 to kernel to m lambda to say 0. Okay, and we have some 0 less than, so this is, let's call it v0, v1, vk. But this is equal to m lambda mod k. This chain will lift to k to whatever, the lift of v1 plus k. I'm calling it v1 plus k, of course, to vk plus k. And now it can be refined. Let's call it 0. Well, actually, this is not for here because this is 0 is the pre-image of K. It can be refined to a chain for M lambda. Right? Because now I can start taking K going containing something else, containing something else, containing. And there is a part here also. And then there is a part from K to M lambda. So now therefore it suffices. So we will show the more stronger statement rather than for every high straight module. We will just show it for the largest high straight. And mu has finite. Sorry, I keep saying lambda, but I thought there was a mu. Suddenly I changed lambda, mu to lambda. And now I will apply this Jordan-Holder theorem. So I want to use the Jordan-Holder theorems. I want to give you an actual number that works for every single. So for given a module mu, or given high straight mu, I want to give you one number, one integer n. So that every chain for mu has length at most n. What is this number? Okay. Here is the thing. I will tell you the number, and then that is sort of going to bring together what we did yesterday and day. Okay, so maybe fine. Now let me switch to lambda. I somehow, in my mind, lambda is the fundamental, the original highest weight, and all the others are sort of, well, you will see that. Right? I can do better than this, but fine. Now, first of all, remember, every this is object in O, and every object in O is finite dimensional H-weight spaces. This is just the constant partition function or 0, as we said. So the summation of finitely many numbers, the while group is finite. So this orbit is finite. So I'm taking a finite sum of finite integers. This is a finite integer itself. And I claim this is the upper bound on the length of any chain. When I say works, I mean this is the upper bound for any Jordan-Holder chain. Why? So it remains to prove this, and I will stop after. So why is this true? So suppose I have a chain. Say 0, whatever, and 0 is then 0, and then 1, and so on. Suppose I have such chain. Take a particular subquotient. So now okay, but no, let me take such a chain. Fine, take a subquotient. Then look at the so let's look at mj plus 1 mod mj. Let's look at the weights of this. These are contained in the weights of this. You are quotienting out something, so at the most the weights will reduce. Remember, all submodules, whether or not they're finitely generated or category, they are H semi-simple. This is H semi-simple, this is H semi-simple, it's a submodule. You may kill off some weights. So at the most you kill off, so it's contained in the weights of this. This is contained in the weights of M lambda. Because it is itself a submodule of M lambda. In particular, this guy, the weights of this are contained in this cone, lambda minus whatever. So there is a maximal weight. So there exists a maximal weight. Let's call it mu. Let's say mu j in weights of this guy. Is that clear? Because they are contained in a cone, so you go up. You have to get out of the cone at some point. We have done that, drawn that picture on the first day and today. There is a maximal weight in here. But now what do I do? Let's look at this. What does this mean? It means that mj plus 1. So that means that if you take some, let's say, v mu j in this weight space, is a maximal weight vector. Because if you apply any raising operator to it, you will get bigger than the maximal weight. There is no such. That means that eigenspace is 0. So ei times v mu j is 0 for all. But that means that there is a map. So yeah, so it's a maximal weight vector, right? So every subquotient of any chain contains an maximal weight vector. Now consider this. So how does the center of UG? We had talked about the center a long time ago, but this is where it comes in. How does the center of UG act on V mu j and on its lift and it acts in two different ways. Because it's a maximal weight vector, V mu j is maximal. So acts by chi mu j. On any maximal vector or any highest weight module with that highest weight, it acts by that central character. On the other hand, it also acts. We are sitting, everything is inside this Bernoulli. So acts on m lambda by chi lambda. Therefore, acts on any submodule such as mj plus 1 by chi lambda. Therefore, acts on the subquotient mj plus 1 mod mj by chi lambda. And hence on V mu j. So it acts by two different central characters on V mu j. How can that be possible? Those two central characters must be equal. And then we appeal to but then this is what Harishchandra's theorem said. Mu j is in the twisted orbit. And so basically what we have shown therefore is, and I'll stop here, but then maybe I can continue for 2 minutes after the break, the tutorial. But what this says is the following. You take any chain of submodules for m lambda. I'm not saying the quotients are highest weight. Any chain. Every single subquotient contains at least one dimension from a weight inside this summation. At least one dimension is contributed by this vector. It is not in mj, it is in mj plus 1. So how is this possible? So at least I have to, every single time I have a chain, have a link in the chain, I have to add one dimension for a vector in one of these dimensions, one of these weight spaces. So how many links can there be in the chain? At most these many. That's the point. Okay. And therefore now the Jordan-Holder theorem applies and we So maybe I will, as I said, I will elaborate on this step in the tutorial. But that's basically. Okay, so we stop here. And there is a 11-minute break. You can stop the recording. 10 minutes. Sorry.
Yeah.
Okay.
Thank you, sir.
So yeah, I will just maybe I will